Alright guys, I finally found the motivation to make this video. Not really motivation, but more like I have to get it done by tomorrow morning. But anyway, we're going to be starting the last section for the semester, chapter 4, and we're going to get through it, and yeah, that should be it for this semester. As far as exam 3 goes, I still need to go through and add points for your partial credit, so be on the lookout for that. That'll show up tomorrow. But anyway, let's get started. So, chapter 4.1 starts with a pretty happy section, and then it gets a little as we go on. But we're first going to start with the idea of one-to-one functions. So, in the past, when we were dealing with functions, way back in the beginning of the semester, a function was every x value, it was okay for every x value to go to two y values. So that was perfectly fine. Sorry, that wasn't. Sorry. You know what? I'm going to do this. So this is an example of something that's not a function. I blame the quarantine. Okay. So this case would not be a function. Because one button is doing two things. One button can't do two things. Whenever you press a button, it can only do one thing. So that's an example of something that's not a function. Whereas if I draw the other picture, which is what I intended to draw in the beginning, it's okay for two buttons to do the same thing. So this is a function. And it's a function because it's okay for two buttons to do the same thing. And that's what we talked about in chapter 2 at the very beginning of the semester. Now, on that note though, this is a function, but we're going to define a new function. This idea of two buttons doing the same thing, yes, it's a function, but it's not what we call one-to-one, which is the definition here, a one-to-one function. So this is good, but not one-to-one. What a one-to-one function looks like is it's still a function, but every button only does one thing. So this is still a function, but we would say that this is one-to-one. So each button does one thing. And no other button does the same thing. So imagine if you bought a TV and you had your remote control and you lost your remote and then you had to buy a new TV because there was no other way to turn it on. So that's what we're talking about for a one-to-one function. No other button does the same thing. So if you have that, this is what's called a one-to-one function. Okay? So now we have three different categories. You have something that's not a function. One button can't do two things. So that's not a function. We don't even care about that. Okay? We have functions, where functions are every button does one thing, but it's okay for two buttons to do the same thing. That's perfectly fine. And then you go to over here, every button does one thing, but no other button does the same thing. And that's what we call a one-to-one function. Now, we're not going to get too much into the theory of it, but I want you to identify what a one-to-one function is graphically. On the homework, they're going to give you questions with pictures, and they're going to ask you what's one-to-one. So when we're dealing with functions, we have what's called the vertical line test. And let me go, I have Desmos up here. And so I have a bunch of functions, and the vertical line test is as long as any vertical line only crosses the graph once or not at all, then it's a function. So the vertical line only crosses once or not at all, so that's a function. Same thing here. The vertical line only crosses once or not at all. Here at 0, it doesn't cross at all because it's a vertical asymptote, but it's okay. I can do another function like this, x cubed. That's also a function because the vertical line only crosses once. Then we move on to something a little fancier. Same thing though, the vertical line only crosses once. And then we go to the last one. And same thing, the vertical line only crosses once wherever it does cross. And so all of these are functions. But now which ones are one-to-one and not one-to-one? So to tell that, instead of doing a vertical line test, we're also going to do, so vertical line test is what we did before, but for it to be one-to-one, it also has to pass the horizontal line test. It has to pass both. All right. And so here's just a quick example. A one-to-one function, notice that it passes the vertical and it passes the horizontal, whereas a parabola would not pass the horizontal line test, and this is not one-to-one. All right. So going back to Desmos. Okay, so let me turn this off. So if we go to x squared is not one-to-one because notice it fails the horizontal line test. What we mean here, let me go to a nice happy number, 4. Okay, so what we mean here is that there's two x values that do the same thing, namely -2 and 2. So if I was to do a box here, and the answer is 4, notice that we end up with 2 buttons doing the same thing. So both of those x values, 2 x values do the same thing. And thus we would say it's not one-to-one. And so in short, if it fails the horizontal line test, it's not one-to-one. All right, so let me try to erase this and wipe screen clear. Okay, yeah, that's useful. All right, so that's not one-to-one. Let's go to this one. Is this one one-to-one? So notice that I scroll through. It's only touching once, only touching once. That it doesn't touch at all, that's okay. Only touches once. So this shape is a one-to-one function. What about this shape? It turns out, look, it's only crossing once, only crossing once. Here, it only crosses once, even though it gets really flat, and then it only crosses once. So this is one-to-one, but not all x cubes are one-to-one. I just add minus 4x to it, this next line, and notice that this is very much not one-to-one. It crosses 3 times. Okay? Now we're going to deal with this kind of question later in the lecture. And so this is a one-to-one function, because if you zoom out, you can see it still has that same shape. And it only crosses once, doesn't cross at all, that's okay, only crosses once, and there you go. So again, that you have the vertical line test makes it a function, horizontal line test is it's one-to-one. Okay. So anyway, why do we care about one-to-one functions? Well, the main thing is security. So any kind of ID, you have u, and any kind of ID. Let's say, I'll just say credit card. All right, so the way it works is you are tied to that credit card and no one else is tied to that credit card. Well, I guess credit card's a bad example because people borrow them. But you know what? I mean, it works, but you have to get into the actual numbers of it. Let me go with something else. So everyone here has their Collin ID. There we go. All right. So your Collin ID, you know what? I'm going to draw a little cougar. It's not a cougar, it's a cat. But that's my attempt at a cougar. All right. So everybody has their Collin ID number. You are connected to your Collin ID number and no one else has it. So no one else has your number and your number is only attached to you. So if I had a database of your names, I could use your name to find your number, or I could use your number to find you. It's the same thing with your driver's license, your social security number, anything like that. Those are considered one-to-one functions. So any form of security or identification is one-to-one functions. We need those. Databases, if you ever want to look something up, you need to have a one-to-one function. For instance, the Dewey Decimal System for the library. Each Dewey Decimal number, by the way, Dewey was named after a cat. But anyway, the Dewey Decimal number is tied to a book, and that book is the only book that has that Dewey Decimal number. So they're kind of woven together. Only one book has an ID. Each ID is tied to one book. All right. So why do we care about one-to-one functions, though? We could really go on about them forever, but in this course, all we do is introduce it so that we can get to this idea here. The reason why we care about one-to-one functions is that they're needed to define inverse functions, which is the main topic for today. So an inverse function has to start off by being one-to-one, which is why we had to define it earlier. Okay? If it's one-to-one, then another function, which is this guy. Now I want to make a quick note. The notation for the inverse okay, it's f with a little -1 here of x. Now I know it looks like an exponent, but this one is actually not an exponent. Okay, so that means that it's not 1 over f of x. If it was an exponent, that's what you would get. But no, it is not an exponent. Okay, it's kind of weird. It's a convention that was adopted, and now, after people do it for a couple hundred years, you just do it. It's kind of silly the way they write it. In trig, they actually don't use the -1. They use arc in front of the word, arc sine, arc cosine, to avoid the confusion. But in algebra, usually when someone introduces an inverse, they'll tell you that it's an inverse, so you know that that -1 is not an exponent. It's just a symbol. All right? Anyway, so that's the weird part. But what an inverse does, so let's say my function, and I'll use your Collin ID. Let's say the function is using your name, and let me put f of x in front of it. So the function I would call f of x. And let's say that what I'm doing is I'm using your name to find the Collin ID, your CW ID. Okay? Now the inverse, which we denote as f inverse x. Notice I didn't even say f to the -1. I just said f inverse x. What that does is it uses your CW ID to find your name. So my regular function goes from x to y. My inverse goes from y to x. It goes back where it came from. Okay? Another way people draw it, I'll get to these pictures I have to the side, is they have their f, or sorry, not f. They'll have the domain, they'll have the range, and f takes you from the domain to the range, whereas f inverse takes you from the range back to the domain. They undo each other. Okay? So if f is putting on your shoes, let's say you get out of bed, or so you wake up, you get out of bed, you put on your socks, and then you put on your shoes. We'll pretend that, it's okay to walk out without any shirt on. So what the inverse does is it does the opposite. Imagine you're done for the day, and it's just not the opposite. You don't go to sleep, then get in bed, then take off your socks, and then take off your shoes. So it's not just literally undoing everything. You undo everything, but in the opposite order. So after you get home, take off your shirt, whatever, get ready to go to sleep, you're going to take off your shoes. So the opposite of put on your shoes is take off shoes. So that's that one. And then you do the opposite of put on your socks, which is going to be take off your socks. And then the opposite of get out of bed would be get in bed. And then the opposite of waking up, running out of colors here, would be go to sleep. So that's what an inverse does. It undoes everything in the opposite order. Anyway, to these pictures, notice what's happening is f sends a to 3. The inverse sends 3 to a. It goes back where it came from. Okay? Same thing. B goes to 1. In the inverse, 1 goes to B. So, real quick, let me erase this. You know what? I'm going to leave it up. Let me see. I think I define it later. I just want to be sure. Yeah. Okay, I define it later, so I'll get to it. Okay. Anyway, so that's what an inverse idea is. So for the inverse, your x's go to your y's. And then notice we swapped them. And then the y's go to the x's. I'm going to relabel it later, but for now, that's kind of the main idea of an inverse. It's something that undoes an action. So, find the inverse of the following functions and state the domain and range for both. So, here's a bunch of x values. So, for instance, 1 goes to 2, negative 3 goes to 5, negative 2 goes to negative 4, 0 goes to 3, 6 goes to 6, 4 goes to 7, 9 goes to negative 2. What the inverse does, which I'll call it f inverse, is it gets these points. And now these points, the order of the points doesn't matter. It's not like a specified order. So all this is doing is, if this is f, didn't get myself room. If f is moving from x to y, then the inverse goes from y to x. So what my inverse is going to do is it's just going to go the other way. Okay? So when I write my inverse, I have to look at where I'm starting. The first point starts at 2 and it goes to 1. So the y value goes to the x value. So I'm going to put 2, 1. The next point goes from 5 to negative 3. The next point starts at it goes from negative 2 to negative 4. So the inverse does the opposite. It goes from negative 4 to negative 2. The next point, if it went from 0 to 3, now it's going from 3 to 0. Next point, 6 goes to 6. Notice this stays the same because the values are the same. Next point, 4 goes to 7, so therefore 7 goes to 4. The last point, 9 goes to negative 2, so therefore negative 2 is going to go to 9. And that is my inverse. There you go. Now, as far as domain and range go, let me write here it's kind of hard for me to fit everything. Story of my life. Okay, so if I have the inverse, what I'm going to do is write the domain and range. I'm going to put the domain on the left and the range on the right. So for my domain, let me write it higher up. So for my domain for f, their domain is just the x values. Okay, you can they don't have to be in order, but the way my brain works, I'll get mad at myself if I don't put them in order. Negative 3, negative 2, let's see, 0, 1, and then 4, 6, 9. Now, what's the domain of the inverse? Okay, notice that we just picked all the x values, and it's the same thing. The quote, quote, x values of the inverse are what the domain are. It's the first value in the list. You know what? I'm going to make these a different color so I can show you something. But notice it's the first value. Whenever they say domain and they give you points, the domain is always the first number in each coordinate. And so here we have, smallest number would be negative 4, negative 2. Negative 4, negative 2. And then 2, 3, 6, 7. All right. So there we go. I have my domain for the original, and I have my domain for the inverse. But what do you notice about the domain for the inverse when compared to the range, which I'm going to write over here? So the range of my original, well, when they say range, they just mean the y values. And notice that since I flipped them, the y values from the original are the x values of the inverse. So the range is going to be the same that I put over here. Negative 4, negative 2, 2, 3, 6, 7. Also, the range of the inverse since all I did was flip the values, the y values in my inverse were the x values for the original. And so I just copy that over. So we can see that there's a relationship between the domain and range of the two. Ran out of room. But anyway, So what we notice is that the domain of f is equal to the range of f inverse. This is an important relationship. Because if I swap the x values, they become the y values of the other function. Okay, the domain of f inverse is equal to the range of f. Anyway, so again, a cool observation is if AB is a point on the graph of f, then BA is a point on the graph of f inverse. 1, 2, 2, 1, negative 3, 5, 5, negative 3, negative 2, negative 4, negative 4, negative 2. So that's the observation that we found. But then also notice that there was one point that stayed the same. 6, 6 stayed 6, 6. And that's the same for any point. So it turns out that if I have AA for my f, the inverse will also be AA. Well, it turns out that that's a line that I can draw. 0, 0, 1, 1, 2, 2, 3, 3, and so on. And if you connect all those dots, basically all points that are where the x and y values are the same, we get a line which for inverses is going to be our axis of symmetry. Okay? So I want to show you on Desmos this real quick. So let's say I have the equation y equals x cubed minus 2. I'll just put, you know what, I'll put minus k to show you something. And what I'm going to do is I'm just going to literally switch the x and y values. Instead of y equals x cubed minus k, I'm going to say x equals y cubed minus k. And notice when I do that, I get a graph. Oh. And let me change the colors of these. So I'll make this one blue, and I'll make this one red. Okay? But notice that they have a symmetry, and that symmetry is along the line y equals x. So this is the axis of symmetry for inverse functions. And I'm just going to hit play so we get a cool picture. Notice that it stays the axis of symmetry no matter how I change the graph. As long as it's 1-to-1, the function and its inverse will stay there. All right. So that's a cool one. I can make another one. Let's say I had x cubed. Let's say I had x minus k, x plus 2. Just made something up. And the inverse will literally just swap the values. Y minus k over y plus 2. And so notice with these, still kind of cool, but they share that axis of symmetry is a perfect divider of the two, and yeah, they have symmetry. I think it's cool. All right, anyway, another thing is in this section, you're going to be seeing quadratics, but remember that when we were dealing with quadratics, that wasn't 1-to-1. So they do something special. Oh, I did caps lock. Okay. So we can't do this. Notice that I can say x equals y squared. So you might say, well, I'll add plus k just so like you can see I'll move. Well, notice that the symmetry is still there. So the question is, why is that illegal? Why can't I do that? And the answer is, well, you can't do it because this parabola right here is not a function. It fails the vertical line test. And so because of that, it's not a function. So if the original function fails the horizontal line test, then the inverse will fail the vertical line test. So that's why they have to be one-to-one. So what they do in your problem when they give you quadratics is they do what's called restricting. They get the parabola, but they only look at half of it. They say, all right, I have a parabola, but only the right half. If you do that, basically chop it off, then yes, you have a one-to-one function. Same thing here, all the x's and y's swap. And so if you do that, then yes, you have a one-to-one function. And so on the homework, you will be seeing problems, but whenever you see a quadratic, it's not the full parabola, it's just half the parabola. Okay? And it doesn't have to be just greater than 0. They could have said less than or equal to. And then this would be less than or equal to. Yeah, good stuff. All right. Anyway, let's create our own graph in this example. So what I have here is a picture, and we're going to graph the inverse. We're going to label the axis of symmetry. So first, let's start by drawing the axis of symmetry. The axis of symmetry is 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. Basically, every point along the line y equals x. And all you do is you connect the dots. Oh, sorry, as a dotted line, because it's it's not really there. It's just used for visual reference. And so remember, this is the line y equals x. So there's the axis of symmetry. And now we're going to graph the inverse. And all the inverse does is it gets all my points and it swaps them. So this point here is -8. Let me zoom in. -8, -8. So then the inverse is also -8, -8. We go to this point. This point is -6, -2. So the inverse is going to be -2, -6. So all you do is you swap the x and y values. -6, -2 had an open circle, so -2, -6 is going to have an open circle. The 2 points are connected with a line, therefore the 2 points are also connected with a line. Okay, then I just keep on going. This point is -6, 1. So then you're going to have a point at 1, -6. Here is -2, sorry, 0, -2. So then we're going to have a point at -2, 0. Now those points are connected, so therefore these 2 points, wow, I did that really bad, are going to be connected. I need a straight edge. I'm getting mad at myself. Terrible lines, Gilbert. Okay. This point has an open circle at 0, 2, so open circle at 2, 0. Here we see that there's 3, 5. So then at 5, 3, I'm going to put a little point there. And notice that it's like a circle toward it, so I do a circle toward it. And then the last point, this arrow points to 8, 7. So then I'm going to have a point at 7, 8, and that's where my arrow is going to point. And there you go. Now on your homework, it's not going to be as clear cut as that. They're not going to make you do it manually. They're going to show you 4 pictures, and they're going to say which picture has the function along with its inverse. And basically, you just pick the graph where the axis of symmetry is y equals x, and the left side is symmetrical, sorry, the upper left side is symmetrical to the lower right side. Okay? It's kind of lame, but they just have you pick the correct answer. If I was giving you the test on paper, like in class, you would have to do it your own. And all you do is just flip the points and graph it. All right. So let's keep going. We're actually almost done with this section, so that's kind of cool. Let me pause real quick. See what my cats broke. I think it's they get confused whenever I start talking like at a normal voice because they don't know who I'm talking to and they just get all excited and freak out. Alrighty, let's finish this section up. So we define inverse, but I didn't get very formal with it. The official formal definition for an inverse is first it has to be 1-to-1, like you mentioned before. Okay, it has an inverse. Notice the naming between the two. If both of the following are true. So check this out. The real definition means if I plug the inverse into the original, all I'm going to be left with that is x. So again, what do I mean by plug in? Sorry. So for second language learners, that's not very fair terminology. If I replace all x's in f of x with the inverse, so if we replace all x's with the entire inverse, then everything cancels. And all I'm left with is x. That's it. So that's the proper definition for inverse. If you replace every single x with the inverse and simplify, all you're going to be left with is x. And it works the opposite. If I replace all the x's in f inverse with f of x, then everything cancels and all I'm left with is x. So that's what these two rules are saying. Okay? Just notice in math, it's very quicker to write it this way. So the math was very concise with its terminology. You just have to understand what it means. But yeah, so you replace all the x's with the other form, and everything should cancel out. And then this is what I was talking about before. The domain of one is equal to the range of the other. So if you have f of x and you have f inverse x, f has its domain and its range. F inverse has a domain and range. But since all you did was swap the variables, the domain equals the range of the other. The domain equals the range of the other. So anyway, how do they test you in this to understand the definition? Well, what they do is they give you two equations and they say prove that they're inverses. Okay? And so to prove them, you got to do two things. I guess I should write it up. Oh, I'll put it here. So the first thing, replace all x's in f of x with f inverse. So that's the first thing we're going to do. So notice f of x. Sorry. And we're going to replace them with f inverse. So if I look at f is cubed plus 1. I'm going to replace it with the inverse, the cubed root of x minus 1. And if it truly is the inverse, everything should cancel. Whoa, kitties, you alright? Alright. Gus cornered Montana, and Montana being cornered, I think she screeched at him or did a hiss at him. Uh-oh. Now they're staring at each other. Hold on, let me throw something at it. Stop it. There we go. I threw a fork across the living room. Anyway, so notice that everything starts to cancel out. The cube root cancels with the cubed, and you're left with x minus 1 plus 1, and then the minus 1 plus 1 cancel, and you're left with just x. Yeah! So that's the first thing you got to do. The second thing you got to do is replace all x's and f inverse with f. And so this is the same idea, except now it's f inverse with f of x on the inside. And so if it truly is an inverse, both ways will work. So the inverse is, or f inverse is the cubed root of x and then minus 1. And so what goes here is f of x. Okay? And if it truly is the inverse, they'll cancel each other out. And they do. And so since it worked both ways, then I can say therefore are inverses. Okay. Now on the homework, they might not call it f inverse. They might call it g of x, because if they tell you it's the inverse, they're kind of already giving it away. But if you work it out, if you get x, then they're inverses. But it has to be x. It's not just that they're the same. It must be x. There's a question on the homework that tries to trick you. And you work it out, and you do it one way, and you get 1 over x. You do it the other way, and you get 1 over x. And you're like, oh, look, they're the same, so they must be inverses. And no, they're not. Okay, because the answer has to be x, not anything else. Anyway, let's look at this one. I have f of x equals blah, f inverse of x equals blah. Now this one I picked just because it's fun, because I'm evil. All right, so for this problem, to prove that they're inverses, I'm going to start with f of x, and I'm going to replace all of the x's Let me move this down. I'm going to replace all the x's with the other equation. So I replace the x's with 4x minus 3 over 2 minus x. And now we simplify. So this simplifying looks really scary, but what I'm going to do is I'm just going to get rid of the denominator, or the inner denominator. And I do that by multiplying everything by 2 minus x, by whatever the denominator is. Everything gets the 2 minus x. Okay, when you do that, all that happens is the 2 minus x is cancel, and you're left with 2 times 4x minus 3 plus 3 times 2 minus x all over 4x minus 3 plus 4 and then 2 minus x. And then from here, it's just simplifying. It's annoying, but it's going to work. And so we work it out. We get 8x minus 6 plus 6 minus 3x. On the bottom, you have 4x minus 3 plus 8 minus 4x. And notice the 6's cancel, the 4x's cancel. And you're left with 5x over 5. And that's equal to x. Yay! And so we do the same thing, but on the other way. Now I'm going to do f inverse and replace all the x's. So f inverse is 4 minus 3 over 2 minus And I'm going to replace all of the x's with the other equation. So 2x plus 3 over x plus 4. 2x plus 3 over x plus 4. 2x plus 3 over x plus 4. Okay, in the same manner, I'm going to multiply by the inner denominator. So x plus 4 Okay, the denominators cancel here and here, here and here, but I have to write it out everywhere else. So I have 4, 2x plus 3, minus 3, x plus 4, over 2, x plus 4, minus, now notice the minus sign will still distribute, so I still need to put the parentheses. And so here I just have everything distributes everywhere. We have a big distribution party. So I get 8x plus 12 minus 3x minus 12, and then 2x plus 8 minus 2x minus 3. And notice the same thing happens. The 12 minus 12 cancel, 2x minus 2x cancel, and you're left with 5x over 5 again. Okay, so it seems kind of annoying. You might not say, well, why do I have to do it both ways? Well, that's just the proper way to do it. To formally prove it, you have to show it both ways. You plug them into each other, and you want to get x at the end. To show you an example of why, it's kind of hard to find a counterexample, but technically there does exist counterexamples. So, for instance, and I'm going to be sad if it wasn't even recording at all. Okay, no, it was recording. Okay. All right. For example, f of x equals x squared. And I know this one is kind of No, I don't think this is going to work. I need to find a proper counterexample to show you. Because if I do it this way, it does work. F of g of x Okay, now that works. All right, well, remind me to find a proper counterexample, and I'll find one that works. Because we can't do the whole thing, because then that's not a one-to-one function. But for now, trust me, it slipped my mind at the moment. But there do exist counterexamples. Anyway, so that's the boring part. That's okay, having to prove that they're inverses. The part that you use mostly later in math is finding the inverses yourself. And this is what this next section is over. Okay? So what we're going to do is how to find an inverse. The first thing you're going to do is replace f of x with y. So for instance, I'm just going to make up a really quick example. So the first thing you do is you replace f of x with y. and then you swap. And so when you swap, what happens is you get, I'll just write it underneath. X equals y minus 3. So when we swap variables, okay, as it turns out, the act of swapping literally is the inverse. So for instance, y equals x minus 3, x equals y minus 3. Okay, those are inverses. Notice if I do y equals x, the axis of symmetry, they're perfectly symmetrical to the axis of symmetry. So the act of swapping the variables gives you the inverse, but you have to get it in the right form. You got to get it in y equals form. So after you find the inverse, what you're going to do is you're going to solve for y. And here, all I got to do is add 3. And I have y is equal to x plus 3. Okay? To finish it off, you replace the y with the f inverse. So you have f inverse equals x plus 3, where f is equal to x minus 3. Anyway, that's the easiest of easy examples, but let's do one that's a little harder. So find the inverse of blah and blah and state the domain and range. Okay. Well, first let's look at the domain and range for this f. The domain is just negative infinity to infinity. Why? Because it's a parabola. We dealt with parabolas in the last section. Parabolas are polynomials. The domain of a polynomial is negative infinity to infinity. Notice that this is a parabola, and it goes left 3, up 7. So that means the range, going left 3 doesn't change the domain, but going up 7 does. The range is going to be 7 to infinity. All right, anyway. Notice that I used tactics from previous exams to come up with those. All right. Oh, but you're right. I almost caught myself. I almost messed myself up. Left 3. If I put left before, I apologize. Right 3, up 7. So just to point out, when they give you these problems, if I graph that, two x minus 3 squared plus 7, notice that it's not 1-to-1. So what I got to do is I have to chop off half of it. Well, I chop off half of it means x is greater than or equal to 3. You can either pick the right half or the left half. See? Okay. Sorry about that. Turned off notifications. Don't want Gilbert's dating life to make its way into my lectures. Okay. So we have the point 3, 7. And so I just want the right half of it because it's a parabola. So it was a typo in this handout. I should have clarified and I should have said for x greater than or equal to 3. So my domain is actually not negative infinity to infinity. My domain is 3 to infinity. Okay, anyway. So to find the inverse, what we do is you change the f of x to a y. and then we swap. So when we swap, this becomes x equals 2 y minus 3 squared plus 7. All right? And now all we got to do now is solve for y. Okay, so to solve for y, we just subtract 7. Divide by 2. Take the square root. Okay, and notice it's plus or minus, but since I'm only dealing with the positive side of my graph, I'm just going to use the positive side of the square root. And it would probably be helpful if I didn't cram this toward the bottom. All right, so y minus 3 equals the square root of x minus 7 over 2. And then the last step is to add 3 over. So if you leave it like this, you're actually going to get minus 1 as far as your score goes. Because the very last step, once you have y by itself, they want you to replace the y with f inverse of x. And then you have your final answer. All right, so there you go. We have the original function. You swap the variables, solve for y, and you end up with the inverse. Now they want you to find the domain and range of the inverse, but it turns out if you know the domain and range of the original, you know the domain and range of the inverse. So automatically I know that the domain is 7 to infinity, and the range is 3 to infinity. They swap places. All right, so that was that example. Let's go ahead and do the next one. So now I have y is equal to, I'm going to go ahead and, well, first let's start off with something. Notice that they also want the domain and range. So if I look at this equation, we've already had enough exposure with these where I can kind of tell what the domain is right away. I know the domain of f is everything but negative 4. So negative infinity to negative 4, negative 4 to infinity. All right. Now the range, I'm going to keep that open because I don't know what that is yet. I knew the range earlier because I knew what a parabola looked like. Now this one is a little more So anyway, we start off by replacing the f of x with y. And then we swap. And when we swap, we get x is equal to 2y minus 3 over y plus 4. Now, when you do that, now we have to solve for y. I like this problem because it throws people off. They get confused and like, what do I do? How do I solve for y? Notice that there's 2 y's in the problem. Your final answer only has to have 1 y. So the first step, usually most people get right. They multiply by y plus 4. All right, now I'm going to go ahead and distribute. Xy plus 4x is equal to 2y minus 3. But the mistake I get is that people will solve for a y. They'll get this y and say, oh, I just add 3 or divide by 2. Or they'll get this one and say, oh, I just minus 4x and divide by x. But you can't do that. You have to get all the y's on the same side. So what I'm going to do is I'm going to get my y's on the same side. So let's say I'm going to get this term. Well, it doesn't really. Well, here's my y's. Here's the things that aren't y's. And you just want to get everything on the same side. So what I'm going to do is, let's see, which side would look better? Okay, I'm going to move this over here. It's a positive, so I'm going to have to do it with subtraction. I'm going to move this over here. It's minus, so I'm going to have to do that with addition. So when I do that, I get 4x plus 3 is equal to 2y minus xy. So the reason why we wanted to get all our y's together is that now we can factor it out. Okay. So I have 4x plus 3 equals y, parentheses 2 minus x. And then I can easily solve for y by just dividing by the 2 minus x. So your final answer, you don't write y equals, you have to put f inverse equals. And notice we have 4x minus 3 over 2 minus x. Okay, so all's well and good. We have the original function, we have the inverse, but now I got to find the domain and range. And this is where knowing your stuff kind of comes in handy. I'm going to do my computer magic again. Uh-oh. What was that too? I don't know where that was. You know what? I'm just going to fill it in. Okay. Oh, God. It's a long night. Oh, that was the 4 is what I had chopped off. Oh, got it. Okay. Anyway, so we went ahead and we solved it. And now I got to find the domain and range. But this is where the play between the domain and the range come in handy for inverses. So if I know the domain of this one, the original, I automatically know the range of the original. It's the same thing. Okay. Now I have no idea what the range is for the original, but looking at this, I can see that x can't be 2. 2 minus 2 is 0. So the domain of the inverse is negative infinity to 2 to infinity. Okay? Which means that these have to be the same. So that means my range is really negative infinity to 2 to infinity. So notice how I found the range after the fact. In the previous problem, I knew what the domain and range were from the very beginning. So I knew the domain and range of my answer. Here, I didn't know the domain, but I didn't know the range, but the domain gave me the range for the answer, and the domain of the answer gave me the range for my original problem. Anyway, so this is the hardest that they're going to get for this section. And really the hard part is just knowing how to solve this equation that has 2 y's in it. Anyway, last page, and then we are done. So This is just a word problem, and you're going to see one almost very much like it on the homework. The function defined by f of x equals 9/5 x plus 32 gives the temperature in Fahrenheit based on the temperature in Celsius. So that means that this right here is the temp in Celsius. I always misspell Celsius. Right? Determine the temperature in Fahrenheit if the temperature in Celsius is 20 degrees Celsius. Well, that's happy. That's just plugging it in. That's just f of 20. And so you get 9/5 20 plus 32. And you know what? Let's go ahead and get the calculator out. And so all we do is we plug it in. So 9/5 times 20 plus 32. 68. So 20 degrees Celsius is 68 degrees Fahrenheit. So that's a very nice temperature. Hey, that's a good sleeping temperature. That's what I keep my house at when I go to sleep. Write the function representing the inverse of f and interpret what it means in this context. So now they want me to find f inverse. So if f of x equals 9/5 x plus 32, okay, they want me to find the inverse. So I'm going to do exactly what I did in the previous section. Then I'm going to swap. And when I swap, that gives me x equals 9/5 y plus 32. And now I'm going to solve for y. So this is really easy to solve for y. Notice that I just subtract 32. And so I have x minus 32 equals 9/5 y. And then the last part is just multiply by 5/9. So the 9's cancel, the 5's cancel. And so I have y equals 5/9 x minus 32. You can distribute if you want. 5/9 times 32, I don't think that's a happy number. It might be. No, it's not. Yeah, no. So usually when you see the formula, it's just left like that. And so remember, instead of y though, I replace the y, and I replace it with f inverse of x. And so the question's asking that there's my inverse. Now what is it in terms of the context? Well, if the original problem goes from Celsius to Fahrenheit, another word that I can't spell, F-A-H-R-E-N, height, okay, then the inverse must go from Fahrenheit. So it's an equation that goes from Fahrenheit, can't spell, wow, Fahrenheit to Celsius. Okay, so normally in the US, when we hear other people from other countries say the temperature, we have to use that formula to convert from Celsius to Fahrenheit. But for every other country, when they talk to an American and we say a temperature in Fahrenheit, they use this formula instead to convert from Fahrenheit to Celsius. Okay, so that's that. Now determine the temperature in Celsius if the temperature in Fahrenheit is 23. And so we're just going to use the inverse equation. So 23 degrees Fahrenheit is really cold, below freezing. And so what would that be in Celsius? Which actually makes a lot more sense to the real world, but whatever. So parentheses 5/9, just because I don't being a little paranoid with my stuff there. 23 minus 32, -5. So the temperature would be -5 degrees Celsius. All right. So this is kind of really the hardest the problems get for the word problems get for this section. They're not really bad. They want you to find the inverse, but then interpret what it means. And remember, it's just the x and y values change. So think about what your x value is, think about the y value is, and swap them. So this went from Celsius to Fahrenheit. So the inverse goes from Fahrenheit to Celsius. Anyway, let me know if you have any questions. Have a good day, and time for Gilbert to get some sleep.